Hi everybody, this is the last part of this brief introduction to the object-oriented programming paradigm in the Python language. In the last video, I explored the concept of data encapsulation and delegation. Data encapsulation is related to types, classes, and methods, while delegation is implemented with either inheritance or composition, that is, in an implicit or explicit way. In this video, I will discuss the third main concept of object-oriented, which is polymorphism. First of all, what is polymorphism? As I said in the last video, one of the problems we always have, regardless of the language and the platform, is code reuse. We want to minimize the amount of code we write when implementing a feature for two reasons. First, code is a source of bugs. The more code you write, the higher the chance to introduce bugs. Second, code has to be maintained, which means that when requirements change, you need to adapt it. So, while delegation allows us to reuse code that is already defined in another object, just like a code library does, polymorphism addresses the problem of reusing algorithms or processes. Let's take a simple example from our daily life. Surely you learned how to type on a computer keyboard. But not all keyboards are the same. Some have thick mechanical keys, some have very soft and shallow ones. External keyboards usually have extra keys on the right side, while keyboards on notebooks are more compact, and so on. Though you might not find some of them comfortable, you can still use them. And this is exactly what polymorphism is. You learn to interact with something that is keyboard-like, so you can reuse your knowledge on a different model. Knowing how to type on a keyboard doesn't help you when it comes to play a guitar, for example, even though both require just your hands. Before we dig into polymorphism in Python, let's review an important concept: references. Let's have a look at this very simple log of the Python console. As you can see, here I define a variable a, giving it the value 5 as integer. Well, when I use the name a now, Python knows that I'm referring to the value 5. As you can see, when you ask Python to tell you the type of a, it tells you that it is an integer. And if we dig a bit deeper, we can also know the position in memory where the variable is stored, with the built-in id function. So far so good, and I guess nobody is surprised. Python variables are containers that have a position in memory, and that can contain values, right? What happens if I redefine the value of a? Here, I tell Python that a has the value 5 as a string, and everything still works. Python can give me the value when I name the variable, and when I check the type of a, I receive a matching one. But when we check the address in memory, we discover that it changed. So, under the hood, Python created a new place in memory to store our string, and somehow connected the position of that place with the variable a. If you are a beginner programmer, think about this in these terms. Python variables are not the boxes that contain values. They are the position of the boxes in the shelf. It might sound trivial, but it's a very important difference. All the values in your program are stored in a cupboard, and you label each position of each shelf with a number. Variables are nicknames for these numbers. If you are an experienced programmer, just remember that variables in Python are always pointers. That's it. Very simple. In languages like C or Java, we define named boxes that we call variables, store values in them, and then put them in the shelf, which is the computer's memory. In those languages, you have a separation between variables and addresses. The variable is the box. The address is the position in the shelf. This is not the case in Python, so whenever we refer to a variable a, we are referring to the value stored at position a. In Python, variables are references. Again, it might sound I'm just nitpicking, but please bear with me, as this point is crucial. Let's discuss variables as function arguments. Here I wrote an extremely simple function in Python, echo, which just returns its argument. You might notice that this function doesn't specify any type signature. Nowhere can you find any hint of what a is. And this is done on purpose, as in Python this function works with any type. an integer, a string, a module, whatever. You can see here a first glimpse of the power of references. The function echo that I wrote returns whatever is referred to by the variable a, which is its argument. So when we write a function like sum here, we tell Python, whatever I pass you as arguments a and b, sum them together. Pay attention, we are not saying, dear Python, a and b are two integers, sum them together with the sum integers operator and return the resulting integer. No, we just say sum whatever comes in and return the result. As you probably think I'm rambling about useless theoretical differences, let me show you a practical use of this flexible sum function. Well, the sum function works on integer, no surprise here. It also works on floats. But after all, floats and integers are just numbers, right? Well, it also works with lists, and lists are not numbers. It also works with tuples. Okay, so my point is, echo and sum are polymorphic functions because they do not connect tightly with specific types. We might say that they implement a generic algorithm more than a specific one, and this is the core of polymorphism. An algorithm that is loosely connected with the type of the variables it deals with. Let's take sum and discuss it a bit more in depth. Why is sum polymorphic? How does Python implement this polymorphism? Let's see what happens step by step. Sum receives a and b, and we know those are references. So, as we said, those are positions in memory, and to accept them we don't need to know the type of the value contained there. After the sum is performed, the function will return the value, and this is not problematic at all, as the returned value is once again the position in memory of the result. So, whatever magic Python uses to perform a polymorphic addition, it is in the plus operator. Let's isolate the plus operator and study it. We already know that it works with integers, floats, lists, and tuples. Does it work with dictionaries? Unfortunately no. It doesn't work with mixed types either. So plus is polymorphic as long as the operands can be added together. And by extension, so is our sum function, which relies on the plus operator. How can plus be polymorphic? We might expect plus to be defined somewhere in Python, something like this code here. You see, we have a plus function defined somewhere, and then a series of if conditions. If type of A is int and type of B is int, then return the integer sum of those. Otherwise, if type A is float and type B is float, return the float sum, and so on for lists, tuples, and whatever else we want to sum. You realize that such a function would be gigantic just for the built-in types. Not to mention that any time you define a custom type, this should be changed. This can't be the solution. So how does it work? Let's have a look at a simpler example. Here we have the built-in function len that you probably already know. It returns the length of an object, and we can run it on lists, strings, and dictionaries. If we try to run it on an integer though, we get an interesting exception. It says object of type int has no length. After all, the length of an integer is not defined, right? This, however, reveals how polymorphism works in Python. If we check inside these objects, we can find the len method that returns the length in all of them, but in the integer. So in Python, polymorphism works by delegation. When we need the length of an object, we ask the object to provide it. When we want to sum objects, we ask the object themselves to add. This means that when you create a new type, you can provide an algorithm to sum instances of that type, creating a method inside the object. You don't need to change anything global in Python. Okay, let's try this so you can see it in action. Let's say that we want to create a new type of integer that has a definition of length. The length of this custom integer object is defined as the number of digits, so 5 as length 1, 12 as length 2, and so on. It's silly, but it serves well as a simple example. So here I define the class customInteger. I derive from int, so I get everything comes from that type. I can indeed initialize customInteger into a variable a, so a customInteger 5. Another variable is b customInteger of 12. I can sum them and get the proper result. When I try to run len on a, I get an exception. Nothing new here, as customInteger just derives from integer, so it's basically the same type. But if I add the len method to customInteger, things change. So the implementation of the method is something trivial and not very important at this point. It's just the length of the equivalent string. So 5 is a string with just the number 5, and so the length is 1, and 12 is the string with 1 and 2, so the length is 2. So if I initialize this class and use len of the instance, suddenly this works. Okay, so as you can see here, we are leveraging what are known as magic methods. Those methods which name starts and ends with 2 underscores, called dunder. These are called magic because they are implicitly called by Python when you run built-in operations like mathematical operations, length comparisons, and so forth. But the point I want to make here is that in Python a built-in function like len is polymorphic as long as the object passed to it is polymorphic. So what does it mean for an object to be polymorphic? As you saw in the previous example, customInteger wasn't polymorphic on the len function, which means that len could not understand how to deal with it. When we added the dunder len method to it though, it became polymorphic. The set of methods that an object provides and their signatures is called interface. And while there is no syntax definition for it in Python, it's still a concept. Recalling the initial example, you can say that something is keyboard-like when it has keys organized in a certain way, with letters on top of them, and that is the interface of a keyboard. The same is true for objects. The initial customInteger class didn't provide any dunder len method, so it didn't expose an interface that allowed len to work. But as soon as we add the methods, we have compatibility at interface level, and we have polymorphism. Do you remember what I said when I introduced types? We discussed behavior over structure. We are not really interested in knowing how the object is structured internally. We just want to know if it behaves a certain way. This is exactly the definition of interface. An object behaves a certain way because it exposes a certain interface, that is, specific methods with specific signatures. Finally, let's consider a practical and also useful example. Python has a concept of file-like objects, that is, objects that behave like files. What is the behavior of a file? Well, it can be open, you can read and write to it, you can close it. There are more properties like moving around, appending and so on, but let's keep it simple. Now I have 2 files on my system. One is a plain file that I created with this bash command, and the other is a gzipped file that I created with this other command. If you're not familiar with bash, the first one prints the string "this is the content of a plain file" and sends the output to the file plain.txt. The second one does the same, but first runs the output through the gzip program that compresses the data. To read the content of the plain file, you can write this Python code that uses a context manager. And to read the content of the gzipped file, you can use the following code. As you can see, they are very similar. The important part here is that both open and gzip.gzip file return a file-like object, which means that you can run the read method. Being file-like objects, they are polymorphic, so you can use the same algorithm on both. This doesn't use any magic method, so you can see how polymorphism is a broader concept that allows you to capture the algorithmic part of a process and abstract it, leaving the details of the implementation to the single objects involved in it. This is all for now. If you enjoyed this video, please subscribe to the channel and consider sharing it with others. This is always the best thing you can do, and I appreciate it very much. Also remember that you can ask questions in the comments if something is still unclear, and I will answer or maybe just add another video to clarify the matter. Well, thank you for watching.